Now I just brief the things what we have learned in the last class. That is the slope deflection equation. Usually slope deflection equation consists of three parts. One is the moments due to rotations plus the end moments due to deflection or settlement, and third one is due to end moments due to loading. Okay, so this MAB means this is the total end moment. These first two terms, that is 4EI by L into theta A plus 2EI by L into theta B minus 6, these two terms will be end moments due to rotation. Now this 6 EI delta by L square will be the fixed end moment due to deflection or settlement, and the MFAB means it is the fixed end moment due to given loading. Okay. Now you know that this, if you take out 2 EI by L, you will simplify. If you simplify, you will get 2 theta A plus theta B minus 3 delta by L. This term as it is MFAB. Similarly, if you go for the other end moment, that is MBA, that is again, now here if you look at it, it will be 4 EI by L theta A, 2 EI by L theta B. It will be reversed now. It is 2 EI by L theta A, 4 EI by L theta B. Or if you want to write here, 4 EI by L into theta B plus 2 EI by L into theta A, you can reverse it. And these two terms will be remaining same. This is the moment due to settlement. This is the fixed end moment. And if you simplify that, you are going to get here 2 EI by L, 2 theta B plus theta A minus 3 theta by L plus the fixed end moment. So now we have already derived the first two terms, that is end moment due to rotations. Right? Just I will brief it again. Here MAB and MB are given to you. And due to that, you have to find out theta A and theta B. So you are applying the loads as moments now. We are applying MAB at A and MBA at B. If you split this beam and if you superimpose, you can see here MAB at A for this beam, and at A this is 0. Means net moment will be MAB plus 0, that is MAB itself. With respect to B, if you consider this is 0, this is MBA. Again, net moment at B will be MBA itself. This is same as this one. Now, if you draw the bending moment diagram for this, you know that it is a clockwise moment, hence it is plus. But this diagram is M by EI diagram, so it is M by EI. And this is clockwise, from right side it is negative, so it is again MBA by EI. So you know that slope at any point is the deviation divided by the span, that is by tan theta relation, opposite by adjacent. That is what is YBA? It is the deviation of B with reference to the tangent at A. This is from Moore's theorem. You know that theta A equals to slope at A. That is nothing but the deviation at B with respect to A divided by the span L. This is tan theta A in fact, but for smaller values, tan theta is equals to theta. And you know that the tangential deviation can be obtained by the Moore's second theorem. That is the moment of M by EI diagram between those 2 points, because you are calculating the YBA, you have to take moment about B. So if you take the moment about B of these two diagrams, first diagram is this. What is this? 1 by 2, base is L, height is MAB by EI. Into, if you take moment about B, from here the distance of CZ is 2 by 3 into base, that is 2/3 of L. This is plus, so this is minus, again half base into height will be the area of this triangle, but taking moment about B means the distance of CZ will be 1/3 of base, that is nothing but L by 3. So if you simplify that, you are going to get this relation, and by again theta A is equals to, you got MAB into L divided by 3I minus MBA into L divided by 6I. Similarly, now we have to get the value of theta B. So you know that theta B here, if you look at this third figure, theta B is YAB divided by L. What is YAB? It is a tangent. It is 1 minute. We got theta A as MAB into L divided by 3I minus MBA into L by 6A. Hope you are listening. Hello?
Yes, sir.
Okay. Next, theta b is, again, if you calculate that YAB by L, you're going to get another relation, that is minus MAB into L divided by 6CI, then plus MBA into L divided by 3EI. Okay. Now, actually, these are the rotations developed at A and B due to MAB at A and MBA at B. Okay. Now, if you put them in the matrix form, you know that theta AB, and if you put like this, it will become L by 3EI. This will become L by 6EI. Similarly, here minus L by 6EI, L by 3EI, MAB into MAB. You know that if you multiply this, this is the first row, this is first column. L by 3i into MAB, that is what you are getting here, minus L by 6ci into MBA, that is what you are getting here. Sorry, some problem is there, network problem. Anyhow, similarly, theta B equals to this row into this column, minus L by 6i into MAB, that is what this term, plus L by 3i into MBA, that is what this term. Okay. So, but actually what we want to calculate is the end moments. Therefore, if you do this end moment, this will become this inverse into this. In the last class, that inverse was wrongly typed. Actually, it is minus vertical slash. Okay. So now I have corrected that. And if you put this, it will become this one. Then now, if you remove this L by 6EI from this, you will get here 2 minus 1, 2, inverse of that, again theta A into theta A, theta B. Now, so first the same term I am taking here. Now let me calculate this first, inverse of this. So what is this? L by 6EI, 2 minus 1, 2, okay. Then the inverse of this scalar quantity, just it will reverse, 1 divided by this, means it will become 6EI by L. Now just I have given you some idea for this, how to calculate this inverse of A. Suppose if the elements are A11, A12, A21, A22, 11 means what? Row 1, column 1. 12 means row 1, column 2. 21 means second row, first column. This is second row, second column. Okay. What is it? How do you get inverse here? 1 divided by determinant of A. This is a matrix of cofactors. This is cofactor of A11. This is cofactor of A12, cofactor of A21, cofactor of A22. So how do you calculate determinant here? This A11 into A22, right? This is the multiplication of these two minus multiplication of these two minus multiplication of these two. That is A11, A22 minus A21 into A12. Look here. A11, what is this here? 2. This is A11. Okay. Next, into A22, this is 2 again. Here, look at this. Minus A21 is this. What is this? Minus 1. Into A12 is also minus 1. So if you simplify this, you are going to get here 3. So here inverse of A is 1 divided by determinant. That is L by 6A is inverse of this. 1 by determinant. The determinant value is 3. So how do you get the cofactor here? So cofactor of this is A11 is A22. Means the cofactor of this is A11. The cofactor of this will be this, that is A22. That is 2. Right? That's what I am writing here. Then cofactor of A22, this is, that is this actually A22 will be A11. What is A11 here? 2. I will put here. Next, cofactor of A12, that is this. Cofactor of this is minus of A21. What is A21 here? This one. Look at this. Minus into minus 1, that will become plus 1. That is cofactor of 1, 2. Similarly, the cofactor of this one will be, that is, what is this? A21 will be minus of A12. This A12 is minus 1. Minus of minus 1 is plus 1. That is what I am writing here. So this is how to get the cofactors of the this matrix. So once if you get this, so if you simplify this, 6 divided by 3 means it will become 2EI by L, 2, 1, 2, 1, 2. Next, if you simplify this now, putting the value of this in this equation, MEB by MEB, it will be 2 EI by L, 2, 1, 1, 2, theta A. Now you have to expand this. How do you expand this? 2 into theta A plus theta B multiplied by 2 EI by L. 2 into 2 EI by L is 4 EI by L into theta A. 2 EI by L, 1 into theta B. That is nothing but 2 EI by L theta. Second row, 2 EI by L into 1 into theta A. That is, if you simplify that further, you can see here 2 EI by L into theta A. Next, 2 EI by L into 2, that is 4 EI by L into theta B. So these two are the end moments due to the rotations at A and B, that is due to theta A and theta B. This you have seen yesterday itself. Okay. Now, let me calculate the third term, that is end moments due to settlement. Okay. Now, listen here. This is the figure. Already we know that this is the moment applied at A, and due to that rotation will be downward. This like this. This is clockwise. Here the moment is applied like this, so it gets deflected upward. This theta B is also down. This is clockwise. Now, let me give some settlement or deflection at B. See, and A is also pinned and B is also pinned. If I give the settlement delta at B, now this will be the new portion, which I shown with the brown color. Okay. See here, what you should understand here is delta is very small as compared to L. Delta is very small as compared to the span of the beam. So, but to show here, just I have shown some big amount because the figure must be clear to you. But always, essentially, you should feel that delta is very small as compared to the length of the beam. Now, this is the when the both ends are pinned. Now, if you look at this figure, right? What is this? This is a big beam having a fixed end at both. Now, you know that fixed end means the slope will be 0. So therefore, this elastic curve or deflection curve initially come in line with the axis, then it get deviates and it comes like this. Here, if you see here, initially this line comes in line with that, but whereas in at pinned, it suddenly start deviating like this. Okay, that is the difference between the elastic curve at pinned support as well as fixed support. Okay, so to make this deflect downward, you have to here release this and you have to apply some rulers so that it can come down, and this is the amount of delta. Now, so I am superimposing these two figures. That is the first beam which are having pinned ends with this new position of the beam after giving some settlement delta. Now I can superimpose over this one, right? Means what I need to calculate here is the moments required at A to produce theta A due to this settlement. Similarly, moment required at B to produce this delta, and of course, because of this delta, what are the slope developed here? Okay. See now, see what is the slope theta A here? This is the new position now. Always here, axis of the beam, angle between the axis of the beam and tangent is theta A. Now the axis of the beam is shifted once you are given the settlement here. So this is the axis of the beam now. How the tangent comes at A? It comes in line with this one. So the from this is the rotation at A. But here, if you draw the tangent at this tangent will come like this with respect to this delta. When you give delta, the deformed curve will be this one. If you give the draw the tangent at this point, it goes like this. That is horizontal. Then from here, this is from means original axis because it is settlement has taken place. Then to the tangent, this is anti-clockwise. Whereas here you can see here from to the tangent, this is also anti-clockwise. Okay. Now, if you write here theta A from this triangle A, B, and this, if you assume it as B dash, what will be that? Theta A is this opposite side by adjacent side. What is opposite side? Delta. Adjacent side is L. Actually, it is tan theta. As I said, tan theta for smaller values of theta, tan theta is directly theta. It is delta by L. Why it is minus? So we have already taken sign convention. Clockwise rotation as positive, anti-clockwise rotation as negative. So what is the direction of the rotation here, theta A? This is anti-clockwise. Am I right? From to the axis, anti-clockwise. Hence it is minus. Similarly, theta B. This is theta B here. So again, if you continue this triangle, and again this will become delta. So again, this is this line and this line parallel. So therefore, again it is delta by L. But again, why it is minus? See now, this is also anti-clockwise. So both theta A and theta B are anti-clockwise, and here they are, the amount will be tan theta, that is minus delta by L. Okay. Now these are the rotations due to settlement. Now we want to calculate MAB and MBA at the both the ends. Okay. Now we have already derived the expression for MAB. What is that? 4 EI by L into theta A plus 2 EI by L into theta B. Let us substitute the values of theta A and theta B here. What is theta A and theta B? Theta A is also minus delta by L, right? And theta B also minus delta by L. And if you simplify this, 4 EI delta divided by L square minus this also minus 2 EI delta by L square. 4 EI delta by L square minus 2 EI delta by L square. Both minus means it will become minus 6 EI delta by L square. Am I right? These are the two equations. Already we have derived first two terms. This is the end moment due to rotations. Now what are the rotations due to settlement? Theta A is minus delta by L. Theta B is minus delta by L. So if you simplify this, you are going to get here minus 6 EI delta by L square. Am I right? Similarly, what is MBA? It is 4 EI by L theta B plus 2 EI by L theta A. Again, substituting the values of theta A and theta B. Same expressions. So you will get here again minus 6 EI delta by L square. What are these now? MAB is minus 6 EI by delta by L square. Similarly, MB is also minus 6 EI delta by L square. These are the end moments due to what? Settlement. Now we found out two parts. What are the two parts? Now total end moment due to displacement or settlements are rotations and settlement. See now, MAB is, these two terms will be due to rotation. What is that? 4 EI by L into theta A plus 2 EI by L into theta B minus, now due to this settlement. What is this settlement? Minus 6 EI delta by L square. Similarly now, again if you simplify by taking out 2 EI by L, it will become 2 theta A. This is 1, this 1 theta B. This is minus 2 I have taken, so it will be 2 into 3 into 2 is 6. It will become 3 delta by L, because here L is there. 2 into 3, 6. EI delta L into L, L square. It will come like this. Similarly, MBA will be, these are the first two terms due to rotation. Now you have to add this due to this settlement. So now these are the two expressions for the end moments at A and B due to rotations and settlements. Now actually what you know that the total end moments will be due to rotations, due to settlement, then due to fixed end moments. You know, see this slope deflection equation will be due to end moments due to rotations plus end moment due to settlement plus due to loading. Those are called as a fixed end moments. Now look at this. See this, these two are the due to rotations. This is due to displacement. So let me call it as MFAB is the fixed end moment. See, this fixed end moment goes on changing with respect to loading. So we'll see this afterwards how to calculate the fixed end moments. So if you simplify this, we'll get here, if you take out 2 EI by L, 2 EI by L into 2, it will become 4 EI by L, so theta A. 2 EI by L out, it is theta B. Minus, if you take 2 EI by L into, it will become 3 delta by L plus MF AB. Similarly now MBA, what is that? 2 EI by L into theta A plus 4 EI by L into theta B, right? Minus 6 AI delta by L square, it will become plus MF BA now. For BA, it will be BA. For AB, it will be AB. So now we simplify this. Again, it will come like this. 2 EI by L, 2 theta B plus theta A minus 3 delta by L plus A. So if you compare this, you can see here, when it is AB, it is 2 theta A plus theta B. When it is BA, it is 2 theta B plus theta A. But in general, if you want to write, because the span may be BC, span may be CD, like that. If you write MIJ, how do you write now? 2 EI by L, 2 times the theta at this end, that is at I, plus single rotation at J, that is theta J. This minus 3 delta by L plus MFIJ. If I is A, J is B, it will take this shape. If I is B, J is A, it will take this shape. Similarly, you can write for spans BC, CD or something, because you will have continuous beam, you will have 2 to 3 spans in the problem. So depending upon the name of the span, you can go on writing these equations. I hope you understood this derivation part now. Okay. Yes. Can anybody? Hello.
Yes.
Have you understood this? See, here just we have to calculate due to rotations, first 2 terms will come. Due to settlement, third term will come. That fixed end moment is always you have to write it, because as I said, it goes on changing as per the loading on the beam. That part I will take it later. Hope it is clear now. Hello. Okay, thank you. Now the references book you can take, BC Punmaya is there, then basic structural analysis by Reddy is there. I referred one more some IIT videos also. You can refer that also if you want. Otherwise, this material is quite good enough for you. Okay. Now let us see how to apply this slope deflection method for a given beam. Okay. There are 5 steps here. Calculation of fixed end moments for each span. Right? Second is you have to write down the slope deflection equations for each span. I will illustrate this later. Just I am giving you initially steps. Then you have to write the joint equilibrium conditions. With the help of those joint equilibrium conditions, you can calculate the unknown rotations. Okay. Next step is, after calculating these unknown rotations, you have to find out the final end moments, again using these slope deflection equations. Finally, what he has asked, if he has asked bending moment and shear force diagram, you have to draw both. If he has asked only bending moment diagram, you have to draw only bending moment diagram. Okay. Yes. Okay. This I think no derivation is there. You have to remember these fixed end moments. Okay. Look at this. Just I will brief the case. This is the fixed beam with point load at center. Right. See, always at the end A, I told you that is always anti-clockwise, and at the end B, always it is clockwise. Look at this. MFAB is minus WL by 8. I think the derivation part is not there. Just you can remember these formulas. Derivation is also possible. Okay. If you want, I can derive them and I send the notes of those things also. Okay. So, but you have to remember these now, because derivation is not required in this topic. So MFAB is minus WL by 8, MFBA is plus WL by 8. If the loading is symmetric, both end moments will remain same, but with a different sign. Here, second part, this is not a symmetric loading, because with left hand small a distance, with right hand small b. So MFAB, left hand is WAB square by L square. MFBA is clockwise WBA square by L square. Very simple. It is AB square, it is BA square. Right? Again, it is the fixed beam carrying UDL throughout the span, symmetric loading. So both end moments will remain same. So it is minus WL square by 12. It is plus WL square by 12. This is the triangular loading with W ordinate at A. The fixed end moments will be first end anti-clockwise minus WL square by 20, and right hand it will be WL square by 30. Similarly, you can remember all these formulas. Again, I will explain whenever the load comes on that particular span. Okay. So, but you have to remember by the end of the topic, I think you will remember, because you are writing several times these, so that you can easily remember these formulas. Okay. Next. Now we'll take some continuous beams here. because we are solving the continuous beams in this topic along with rigid jointed portal frames. So first let me give what is continuous beam. Can anybody tell me what is a continuous beam? You know already simply supported beam, cantilever beam, hope you know it. Those are the determinate structures. So this is in this subject you are studying the indeterminate structures, right? So what do you mean by continuous beam? Can anybody tell me?
Beams having more than
Beam which having more than two supports.
Beams having
more than two supports.
More than two supports.
yeah, very good. That may be okay, fine. Okay. Now here two spans are there. In terms of spans, we talk here continuous beams. This AB is called one span, BC is called another span. This beam is having two spans. This beam is having three spans. One that is AB, BC, CD. Similarly, this also three spans. Now, can you tell me to call a beam as continuous, what must be the minimum number of spans or supports you can say? To call a beam as a continuous, what must be the minimum number of spans or supports? Anybody? Hello? Hello? Can you hear me?
So support must be 3 equal to 3 or more than 3 is there continuous beam.
Very good, very good. Then how many minimum spans to call a continuous beam?
Two spans.
Two spans, yes. Minimum number of spans must be two. Maximum number may be any n number of supports. You may have 3 spans, 4 spans, 5 spans. You may have any n number of spans. But minimum number of spans must be 2. Similarly, 3 supports must be minimum supports to call a given beam as a continuous beam. Is it clear? Is it clear about a continuous beam?
Yes, sir.
Okay. Then here, what are the unknowns? As I told in the last class, here the number of unknowns will be the rotations of the supports. Okay. Here you need not to calculate decay because decay directly it comes with 3j minus r. Formula is there, and for inextensible it is 3j minus r plus m is there. But here I don't want to use the formulas. See, you know that slope will be 0 where at which support? Slope will be 0 at which support? Anybody?
Fixed support.
Yeah, very good, very good. Always slope will be 0 at fixed support. See here, end A is fixed. This is called extreme end. Similarly, end C is roller. This is also extreme end. See, these are all supports. Maybe roller, maybe simple support, maybe hinge. All intermediate supports we take it as rigid, and slope will be always there at intermediate supports and end supports provided if it is not a fixed one. Okay, you know that if I take the rotations at the joints, here joints are, which are the joints here? A, B and C. Okay, they are supports as well as joints. At this support, what is slope at A? Theta A. What is slope at A?
0.
0. Very good. Means, but slope will be there at intermediate support as well as if the end is hinged, roller or simple, there also slope exists. Means how many unknowns are here for this beam? Theta B and theta C are the unknowns. Is it clear? How many joint rotations are unknown in this for this beam? Slope at B and slope at C are the unknowns. Let me come to this second beam. What is slope at A? What is slope at A?
0.
What is slope at D?
0.
0. Because see now, first here at the extreme end is C, but roller, there is a slope. But here extreme end is fixed.
Fixed.
So slope will be 0 there. Means here out of 4 rotations, theta A, theta B, theta C, theta D, theta A and theta D will be 0. So unknowns will be now theta B and
2.
theta C. Okay, 2, but they are theta B and theta C. Is this clear? Now let me come to the third example. Can you tell me now? There are 4 rotations in fact. Theta A, theta B, theta C, theta D. Which is 0 here?
Yes, sir.
A.
theta A is 0 because the end, that extreme end is fixed, so slope is 0. But the rest of the this D is extreme end, but it is a simple support, so there exists a slope. Means how many unknowns will be there here?
3, sir.
3.
3 unknowns. What are those?
Theta B, theta C, theta D.
Yes, the unknowns will be theta B, theta C, theta D, or you can say rotation at B, rotation at C, rotation at D will be the unknowns. So in this topic, he will ask the questions which are having kinematic indeterminacy less than equals to 3. Means maximum you will get 3 unknowns, not more than 3 unknowns. Suppose if I extend one more span here with last and again simply supported, you will get 4 unknowns. If I extend this CD to DE and ND again, if I mark a simple support, you will get there 4 unknowns, right? But here in this topic, he will not ask you the the problem which is having not more than 3 unknowns. Only you will be getting here maximum 3 unknowns. Okay, I think the idea is clear now. Is it okay?
Yes, sir.
Okay. Now we will go with some simple problem. Okay. So what he has said is analyze the beam loaded as shown by slope deflection method and draw BMD. I will take very simple problem now. A 2-span continuous beam, AB having span of 5 meter, BC having span of BC having the span of 7.5 meter. Span AB is carrying a load of 100 kilonewton at the center, okay, and span BC is having the 20 kilonewton meter UDL throughout the span BC. What are the support conditions here? And A is what? Fixed. Am I right? B is roller, C is roller. Okay. So first you have to identify which are the unknowns you need to find for this particular problem. Okay. Can you tell me now which? Actually only rotations. You have to think of rotations. 3 supports are there, 3 rotations will be 0. But how many of rotations will be 0 you have to identify. Can you tell me now how many rotations are unknown here? Hello?
2, sir.
Can you hear
Theta
me?
A will be 0.
Pardon?
Slope at B is there. Slope at C is also there.
Yes, you need to find out now 2 unknowns, that is slope at B and slope at C. But slope at A is what?
0.
0. Good. Just I have written here support A is fixed, hence the slope at A is 0. Support B is rigid, that is intermediate support, slope exists, but that is unknown now in this case. Similarly, support C is roller, that is also extreme, it is extreme end, right end, but there also slope exists. This theta C is unknown. Is it clear? First you have to identify what are your unknowns. Is this clear how to identify unknowns now?
Yes, sir.
Okay. Now, what is the first step now? You have to calculate the fixed end moments. Okay. So now here each span you have to consider it as a different fixed beam. First, let me consider span AB. Okay. What is the AB span? AB is the span having 5 meter span carrying load at the mid span 100 kilonewton. Okay. Now MFAB, you know that always it is at this end it is anti-clockwise like this. Anti-clockwise means minus. What is the formula? Minus WL by 8. What is W here? 100.
Load.
L is 5. That is 8. If you simplify this, you will get here minus 62.5 kilonewton meter. The FBA for the other end, it will be, if the loading is symmetric, because center means symmetric, it will be minus WL by 8. So this will become plus WL by 8, because at this end the moment will be anti-clockwise, it will come like this. Okay. Then again if you simplify, you are going to get here 62.5, but it is a plus sign. Is this clear? Now next span is BC. Next span is BC. Okay. Now you have to calculate MFAB. Sorry, this is BC. This should have been BC. It is not MFAB. It is MFBC. What is the MFBC? It is UDL. So it is minus WL square by 12. What is this? Minus WL square by 12. Where W is intensity of the UDL. That is 20. L is 7.5. So if you simplify this, you are going to get here 93.75. Next, this is MFBC. I think cut and paste this problem has come. So this is MFBC. This is MFCB. Reverse. Okay. What is this now? It is W. It is minus. So again, it is symmetric. The loading, this will be plus WL square by 12. So this will become plus 93.75. I think it is clear now how to calculate fixed end. First end will be always anti-clockwise minus. That is, we call it as a near end. For any span, first end, left end we call near end, right end we call far end. Near end, anti-clockwise moment, far end, clockwise moment. Or left end, anti-clockwise moment minus, right end, clockwise moment plus. But you need to remember these formulas. Okay, is this clear? So with this correction, this is MFBC, this is MFCB. This correction has to be made. I will make it and I will send this copy again. Okay, is this clear?
Yes,
Hello?
Yes, sir.
You need to remember formulas. You need to remember those. Okay. Next. Now you need to write slope deflection equations. So already I have written theta A is 0, theta B and theta C are unknowns. Okay. So for first span, if I write, what is the formula there? MAB equals to, you have to remember this formula now. 2 EI by L, 2 times the slope at left end, plus 1 time the slope at the right end. You have to remember like this. 2 EI by L common, 2 times the rotation at the left end, plus 1 time the rotation at the right end, minus 3 delta by L, plus the fixed end moment. Okay. Let me substitute the values here. 2 EI. What is L for the first span? 5 meter. Okay. What is theta A? 0. Theta B unknown. Here delta. What is delta actually? It is a settlement or deflection. So in this problem, he has not given settlement of any support. Unless he says the end has settled by this much amount, means you have to consider the delta is 0 for all the spans. In this problem, he has not given any settlement. Means none of the support has been settled. Means delta is 0 for both the spans. So delta is 0 I have put. MFAB, how much I have calculated that? Minus 62.5. In the previous step, I have calculated MFAB as minus 62.5. A is 0, theta A is 0, this term will become 0. Delta is 0, this term will become 0. So now if you further simplify, how much it will become now? See now, 2 EI by L, 2 EI by 5 means 1 by 5 means 0.2 into 2, 0.4. This is 0, theta B. Then this is 0, so we'll get here minus 62.5. Is it clear how to write this first equation? MAB is 2 EI by L, 2 times the rotation at left end, plus 1 time the rotation at the right end, minus 3 delta by L, plus or minus, that is fixed end moment. Whatever the fixed end moment sign you have got, you put there. Now similarly we write now BA, reverse. It is 2 EI by L, 2 times the rotation at this end now. See now, when AB is written, first is A, next is B. 2 theta A plus theta B. Here, BA means first B. So it will be 2 theta B. Next A. It is BA, right end, left end. Here, left end, right end. First left end, second right end. Here, BA means first right end, second left end. This is clear. Just you have to write here. If it is 2 theta A, here 2 theta B. If it is theta B, here it will be theta A. You can see here A and B. That is the here, but B and A. Next, plus is MFBA. Okay. Substitute the values again. Theta A is 0, delta is 0, but MFBA is plus 62.5. 2 EI by L. Same thing here. Again, it will become 4 EI by L. 2 EI by L is 0.4. Into 2 means it will become 0.8. It will become 0.8 EI theta B plus fixed end moment is plus 62.5. Okay. Similarly, can you tell me now for span BC? What is MBC now? 2 EI by L, it is constant. 2 times the rotation at first letter, that is B, left hand, plus single time the rotation at C. Is it clear? Minus 3 delta by L plus MFBC. Okay. Now let me substitute the values. Here theta B, theta C both are unknown. Theta A is not here, but delta is 0. 2 EI by L, 2 theta B as it is, theta C as it is, this term becomes 0. MFBC we have calculated a minus 93.75. If you simplify this, 2 by 0.5 is 0.4. 0.4 into 2, 0.8. This is 0.4 theta C. This is 0. So minus 93.75. Now, can you tell me now what is MCB? Can anybody tell me what is MCB in line with this next equation? What is MCB? Anyone? MBC, you know that? 2 EI by L, good.
Into 2 theta C
Into 2 theta C
plus theta B
plus theta B
minus 3 delta L plus
3 delta by L, right?
plus MFCB, sir.
MFCB, very good, very good. Just you have to interchange the letters. Okay, look at this now. MCB, 2 EI by L, right? First term is C, so it is 2 theta C, plus second term theta B, minus 3 delta by L, this is MFC. Again substituting the values of C and B, theta C and theta B, and delta. Theta C with theta B are unknowns, delta is 0, and MFBC is minus 93.75, but MFCB is plus 93.75. So if you simplify this, you are going to get the equation 0.8 EI theta C plus 0.4 EI theta B plus 93.75. Is this clear now how to write the slope deflection equations? So by practice you will get this, but initially try to understand. Once if you start doing the problems, you will understand this. Is this clear now the idea of writing the slope deflection equation? Yes? Anybody?
Yes, sir.
Is there any doubts here?
No, sir.
Oh, okay, thank you so much. Now we'll third step. You have to write the joint equilibrium condition. So now this is a given problem. What is a joint equilibrium condition means? They are in terms of moments. Here, what is there are two unknowns, isn't it here? Theta B and theta C are two unknowns. So you need two equations of equilibrium. Then you can solve theta B and theta C. So here, at fixed end, whether moment exists or not, first you tell me. If you tell the moment at the fixed end, whether the moment will be there or not.
There, sir.
Yes, moment will be there. If the right end, extreme end is fixed, moment will be there. Similarly, what about extreme end C, whether the moment is there at C or not?
Not there, sir.
Not there. Means the moment at C, that is MCB, will be 0. If the extreme end is fixed, moment will be there. If extreme end is simple support, roller or hinge, anyone may be there, the moment will be there 0. So first condition is MCB is 0. Okay. Next, for joint B, if you take, what is the joint equilibrium condition now? See, there will be two end moments because B means one member is BA, meeting at B is one member is BA, another is BC, right? At B, two moments are acting. One is BA, another is BC. The sum of those two should be 0 because the net moment at that point should be 0. So here for joint B, what is the condition? MBA for the span BA, MBC. The sum of those two end moments should be 0. This is, we call it as a joint equilibrium condition. Okay. Then For joint C, what I said, you know that the end moment is there, what? 0. So MCB is also 0. So you get here two equation. What is the one equation? By writing MBA plus MBC equals to 0, you will get one equation. It will be in terms of theta B and theta C. Similarly, if you write the MCB, that is the slope deflection equation which you already written. You equate it to 0, you will get one more equation, right? That is also in terms of theta B and theta C. So you'll be having two equations, two unknowns. You can easily solve it. Let me see that out. So first equation we'll write MBA plus MBC equals 0. MBA already written, slope deflection equation. MBA is what? 0.8 EI theta B plus 62.5. What is MBC? 0.8 EI theta B plus 0.4 EI theta C minus 93.75. This is equals to 0. Okay, this is the, if you add, already you are written MAB, MBA, MBC, MCB, isn't it? You just write those, what is the MBA you written plus MBC what you written, equated to 0. So if you simplify this 0.8 EI theta B, here 0.8, it will become 1.6 EI theta B. EI theta C is only one term, that is 0.4 EI theta C. So plus 62.5 minus 93.75. You will get here minus 31.25 equals to 0. So this is the first equation which is in terms of theta B and theta C. Is it clear how to write this? You already written for 4 equations, MAB, MBA, MBC, MCB. You just take MBA equals to, you put here. Next you take the right hand side of MBC, you write here, equate it to 0. Add those two, you will get this. This is one condition. What is another condition now? Yes, what is another condition? MCB equals to 0. Very good. MCB equation already you have written. What is that? 0.8 EI theta C plus 0.4 EI theta B plus 73.93.75. Now you have to solve these two equations to get theta B and theta C. The first equation I write as it is 1.6 EI theta B, that 0.4 EI theta C minus 31.25. Next, minus this second equation, what I do is, because I have to make the coefficient of theta B or theta C same, I want to make the coefficient of theta B same. In that case, what happens here? It is 0.4 EI theta B is there. To make it 0.4 EI theta B to 1.6 EI theta B, what you have to do? This is 2. 0.4 into, I think, is it something wrong? 1. Yes, 0.4. Is it correct or wrong? Something wrong here. 1.6 EI theta B, it will be here, right? This is not by 2, it is how much? How much? See, you have to solve these two equations. One is 1.6 EI theta B, 0.4 EI theta C, this much. Now here, theta B, I have to make it 1.6. How much here? 0.4 into 4 if you do. This is by 4 you have to multiply. 0.4 into 4, 1.6. 0.8 into 4, it is 3.2. Right? Similarly, if you multiply 93.75 by 4, you will get here 375. Okay. Next, you minus that, change the sign. 1.6 EI theta B, 1.0 EI cancels. So plus 0.4 EI theta C minus 3.2 means how much it will be now? 2.8 EI theta C. So both are minus here. 375, 31.25. Both minus. If you add them, you will get here minus 406.25 equals to 0. Is it clear? This multiplying equation 2 by 4, not 2 it is. It should be multiplied by 4. So that 0.4 into 4, 1.6. 0.8 into 4, 3.2. 93.75 into 4, it will become 375. So if you simplify this, you're going to get like this. And if you solve for EI theta C, you're going to get here minus 145.09. What is EI theta C? Similarly now, if you substitute the value of EI theta C in any one of the equation, either 1 or 2, you will get here EI theta B equals to 55.804. So is there any confusion here? Slightly you have to do this work because by listening you will not understand. I think this, how to get this MBA plus MBC, is this clear? Equation number 1 is clear? Hello?
Yes, sir.
MCB equals 0. I hope you will get this. Equation 2 is also, you are getting it. Is it clear? Now you solve these two equations at your home. I have given you some idea. I have written here multiplying equation 2 by, you write it as 4, not 2. If you multiply by, those moments you have to superimpose over this end moment. This is the free bending moment diagram due to point load. That is triangle. What is the ordinate? It is 125. It is nothing but WL by 4. From here to here it is WL by 4. This span is carrying UDL. What is the free bending moment diagram for span BC? It is WL square by 8. Not 12, it is 8. You will get 140.625. You have to take this. UDL means parabolic curve. So this point, it is this 140.625 and this is 0. You have to join with the parabolic curve. Under UDL, you know that bending moment diagram varies parabolically. Under point load, bending moment diagram varies linearly. That's why here it is in the span AB, it is linear variation, straight line. Whereas under the UDL, it is a parabolic variation. Is this clear?